parametric equations. Yeah. Woo woo. Any questions over the homework? Sid. Sketch the following the steps in 7. Oh, yeah. Don't worry about the symmetry too much. I mean, we didn't talk about the symmetry at all. But I mean, we can kind of think about this a little bit. Like, so I got this table here. So remember, odd symmetry will put you kind of in the opposite. I don't know how to describe this. Can't even think of how to describe. Anyway, okay, so we know that even symmetry, like if we're thinking xy, this is xt, so it's a little different. But if we're thinking xy, if it's even, it doesn't matter if you put a positive or a negative in, it's going to be the same. So it's that y-axis symmetry. And then if it's odd, then you know it's going to be origin symmetry. You put in a negative, you negate the input, it negates the output. I guess we can think of it that way. So it turns out you get this kind of symmetry here, which I guess I did these examples a long time ago. But this is, I guess, following what they did in example 7. So you can look at symmetry. If we look at the problem that we're given, x is odd, x of t is odd, and y of t is even. So that's why I'm highlighting that one in green. So we're going to get y-axis symmetry. So it's just something to be looking out for. Let's see. I don't know what example 7 said, so I'm looking back through this. So then they must have done something about just looking for trends. I don't know. Anyway, if we take a look as y increases, as t increases, we know that the y-coordinate is going to increase, and it's always going to be positive. So that also tells us a little bit about what this thing is going to look like. Is there any particular part in there? I mean, so it's just kind of this general thing to look at. So there's trends you can look at without actually having to plug in points. Yeah. Oh, okay. I will say this on the AP exam. I have never seen them, because, your calculator, I can't remember if I told you this or it was 6th period. Even though I showed you how to do parametric equations on your calculator, you will actually never have to do that on your calculator during the AP exam. I forget exactly what all the list of requirements for a graphing calculator are, but being able to graph in parametric mode is not one of them. So they will never make you graph on your calculator. And everything I've ever seen on the FRQs, again, I haven't seen the multiple choice, but all the FRQs that have involved parametric equations, they've always provided the graph. So I'm pretty confident that if they have you do anything with parametric, it won't be graphing it. It will be doing the other stuff. Because the graphing it isn't really the calculus part. Anyway, 27, was there a particular part? Oh, so how do you know to use the sine or the cosine for x? And that's exactly it. In this case, since they're just giving us a circle, there's no direction indicated. It doesn't matter. Yeah. Any other questions? Well, can I have your homework then? And would you hate me if we didn't have a reality check today? No. A little bit? All right. I'm sorry. I don't have a reality check.
So I fell asleep doing last call, so can you just ignore that? So 90% of it, like you said, so I still be able
By a lot. I was 7 to 10. No.
But he came through.
I came through and at the end you were 0.
All right, we're sticking with parametric equations today. Oh wait, there's more. All right, let's get that cursor out of the way. Arc length and speed. I don't know what's going on. All right, let's do this thing. So arc length and speed. We've done arc length before. We've done arc length when it's just xy. So recall. I always hated it when teachers said recall. Recall, what if I don't recall? Does anybody recall the formula for arc length that you'd learned previously? I don't know, Gregory might beat you though. There's no R. I think you might be thinking of surface area. Yes. A little bit more. Nope. You might be thinking it, but look what I have written down. It is F prime. He said F prime. I just, I was making it look more like an F prime, so I was erasing it. Integral. That's it. So that is all formula that we have previously learned for arc length. But what if we have parametric equations instead? So we're going to play around with this thing. And what we need to do, so parametric equations, we always have an x of t and a y of t. So instead of having this in terms of f of x, we want either x of t and or y of t. And then also things will be in terms of t. So at the end, we need a dt. So we have to play around with this a little bit. But we can do that. First of all, f prime, that's dy dx. So I will write f prime as dy dx. But that's still squared, all in a square root dx. But then, we learned last time, we can rewrite dy dx as dy dt over dx dt. And of course that's all squared, still in a square root dx. Ugh, I always hate writing fractions. Is there anybody else, like when you have to write a fraction on lined paper and you like, do you skip lines? Do you not skip lines? And the spacing is weird and just makes me uncomfortable. Whoa. Yeah. I had a professor in college who would always, when you went and talked to him, he wasn't writing on a chalkboard. He just used blank printer paper and a fountain pen. Not pencil, a fountain pen. All right. Anyway, now I'm gonna take this thing. I'm gonna multiply by a form of 1, and it's gonna look like this. So I still have this part. But now I shall multiply by 1. And that form of 1 is going to look like dx dt over dx dt. And I'm going to square it, and I'm going to put it in a square root. I know. I don't have to do that. But I'm going to eventually, so I'm going to do it now. And then I'm going to take that form of 1, and I'm going to break it up. Yes. Thank you. They're just not getting along. Alright, so I'm going to take the numerator and the denominator. Whew. We're almost there. Yes.
Why does it change from dx dt? Because you still have dt's in the I think third line, but 4 times.
This one?
Yeah.
So why are these dx dt's?
No, you've got like the integral dx and you've got the integral dt. Why does it change from dx to dt?
Oh, it shouldn't have yet.
Okay.
I got you. Boy, whoo, whoo. These are still dx's. Yeah, I haven't done it. Just math. You know what? You want a dt? Just put a dt. Yeah, that's all. Yeah, that was testing you again, and good job. You guys are very good at catching my intentional mistakes. All right, so now what I'm going to do, this one, I'm going to distribute inside here. So it multiplies by 1. And then when it multiplies by the fraction, the dx dt's will cancel. So what's it going to look like? This. We're going to have dx dt squared plus dy dt squared. That's all in a square root. Oh, thank God no fractions there. And then over here, well, let's just, the square and the square root can cancel out. So I just have 1 over dx dt. So that would be dt over dx. And then I will finally have it. I'm going to cancel out the dx's, and we're going to have what we want. And no fractions either. Yay. It's the only reason I don't like fractions. They mess up the spacing. Well, this dx dt, because it was 1 over dx dt, became dt dx. Oh, this fraction. Whatever. Fine, but I don't have to, I can write it in a single line. It makes me happy. There we go. That's going to be what we use. So, boom. So there's our first cloud of the day. Cloud. We're going to have 3? I think 3 clouds. This is not bad. So the key thing in here is the intersecting part. Your curve cannot intersect itself, except possibly at the endpoints. If it does intersect itself, you have to break it up into different integrals. Now, if you thought arc length was fun before, you're going to love this. Then you're really not going to think this is fun. Actually, it really depends on the problem. Yes?
Okay. Why does it say such that C doesn't A is less than T doesn't B.
You could, but it's stressing the part that it can touch at the endpoints.
Okay,
But you're right, that would say the same thing. Oh my gosh.
I was just wondering if there's like a specific exception to which you can touch the endpoints. Or is it like all the time if it touches the endpoints, it's fine? Did you say possibly?
Well, the point is that the curve can be touch at the endpoints or not. So it can possibly touch at the endpoints or not. And then it's okay. Now we're going to do what we did before with arc length where, well, I mean, we don't have to, but before, remember with arc length, it was easier, depending on the problem, to find the derivative, then square the derivative, sometimes even add 1 to the square of the derivative before you plug it into the integral. We're going to do the same thing here. We're going to find x prime and y prime. We're going to square them first. We're going to add them first. We're going to see if we can do anything with it before we actually plug into that integral. But you don't have to. So, if you've already written that down, you can start writing the problem down. An epicycloid. Parametric equations can make some funky curves. We've got cycloids, we've got epicycloids. I have a picture of what an epicycloid is when you have, it's like spirograph. I don't know if you guys ever played with spirograph as a kid. But you know, you got the circle gear, and then you have a smaller circle gear with little holes, and you put your pen in there, and you go around in a circle, and it makes cool shapes. You were doing parametric equations, and you didn't even know it. Nerd. Oh, that's a compliment. Are you kidding me? Are you kidding me? I'm sorry. I thought this class would understand that's a compliment. No. No? Nerds are great, man. Woo! Does anybody still need the cloud? It's a flower, that's right. If only I had a drawing tool that could help me with epicycloids. I cheated with the circle, as you can tell, but not so good with those freehand pedals. So these are you won't have to know how to find the parametric equations that make an epicycloid. This will be given. But here is the parametric equations to give you that. So we're going to find the arc length. Now I want to play with spirographs. I know, right? They are fun. Remind me after class. I'll go on to Amazon and see if we can get some spirograph. On the workday, if you guys want, you could play with spirographs. It's math, right? Yeah. Really? Oh, those are cool. Oh yeah, so and you can use them in combination with each other. So like you could use one of the circles that has the holes in it and still go around with another smaller circle. What? Have you ever seen them being used? I'm sure we can find YouTube videos. That's important. We'll watch those next. All right, so let's start going with this. I'm going to deal with x first. We'll find the derivative. We'll square it. We'll see if we can do anything with it. We'll go for y. square it. We'll find the derivative, square it, blah, blah, blah. Okay. X of t is given as 5 cosine t minus cosine 5t. So you guys, I won't pause my screen, but I won't talk it out either. You guys try it. Find the derivative, square it, see what you get. See if there's anything you can do to condense it. Once you finish X, try Y. I think that's all we can do with X. Yes. Are we looking at Y or X? For X. Oh. Well, thankfully it's going to work out anyway. For my final thing. You're right. This is positive. Oh, and then after that. Good. Thank you. Now, if we try to add these, you probably already see some stuff. Those Pythagorean identities. So x prime of t squared plus y prime of t squared. There's 25 in both, so I'm just going to factor that out right now. And sine squared t minus 2 sine t. Sine 5t plus sine squared 5t plus cosine squared t minus 2 cosine Godzilla. Cosine Godzilla. Oh, wow, that's cool. So we got a couple of Pythagorean identities showing up there. We got sine squared t plus cosine squared t, which is 1. And then we got sine squared 5t plus cosine squared 5t, which is 1. Still 1. Remember, the angle can be whatever. As long as the angle matches, it's 1. And so, finally, this thing is going to start collapsing. So I'm going to have a 1 plus a 1. The other two terms left over have a 2 in both of them. So if I factor out the -2, I've got sine t sine 5t plus cosine t cosine 5t. I can finally fit it on one line. Can we make this any smaller? Anybody recognize what's inside the parentheses right here? Not a double angle. Yeah. Anybody know what it's going to equal if you don't remember the name of the identity? It's a sum or difference angle for cosine. So it'll be minus. Cosine's opposite. So since it's plus in here, it'll be minus the angles. So I'm also going to do another thing here. 1 plus 1 is 2, obviously. I'm going to factor out a 2 and put it with a 25. So we'll have 50 and then 1 minus, and that'll be cosine 5t minus t. And remember, cosine is an even function. That's why this can work. We don't really know if it should be 5t minus t or t minus 5t. But either way, because cosine is even, cosine of -4t equals cosine of 4t. So do whichever way you want. And then we know that's going to be 4t. We can put that in our integral. So any questions how we finally got here? Oh, see? Told you. These can be fun. They often have, parametric equations often have trig. They don't have to, but that's when it gets fun. You get to use all sorts of identities. So finally, we can plug this in. So arc length, whoops, let me go back to the pen. Arc length is, I'm going to go ahead and just factor out the, maybe I'll leave the 50 in. I don't know. It's in a square root, don't forget. So if we factor out, make sure you factor out square root of 50 and not just 50 in front of the integral. I'll leave it in. So 51 minus cosine 4t, all inside a radical, dt. Oh, we still got 2 problems. Anybody know what one of the problem is? Sid?
What are our limits of integration?
That is one of the problems. What are the limits of integration? We'll figure that out. Anybody know what the other problem is? How the heck do you integrate this thing? Yeah. Well, let's deal with the limits of integration first. Now to do that, I'm going to go back up to the picture. So, anybody still need this before I leave it? All right. Yes?
What was the, when you condense the term, like sin t, sin 5t, when you condense that down into the cosine, what was that called?
It's a sum or difference. You'll either hear it called a sum or difference equation or addition subtraction. Mm-hmm. Any other questions? Anybody still need this? All right. So let's go back to the picture. I don't even know where to begin. Anybody have any idea what the heck to do on our limits of integration? Yes.
Well, we can start by finding the distance on the axes from the origin to like the maximum value by taking the radius of the inside circle, adding the radius of the outside circle, and then sine which is at 45 degrees to get the distance on the axis.
That's an interesting idea. Not bad. We could actually do that same idea, but even easier, though. But actually, I like it. Here's the only thing with it. I mean, and there's nothing wrong with it, but here's why we can do something that'll be a little easier. So he's saying find this distance, assuming that's 45 degrees that I just drew right there. And once we know that, I'm not sure exactly where. Were you like then saying we could?
Well, yeah, but it doesn't work, so it's fine.
It could work. It just gets a little messy. So instead of doing that, why not just use these points where it intersects the axes? Because those are like this first point on the x-axis, the positive x-axis. What are the coordinates for that point? Bottom one. 4, 0. And then, yeah, this one would be 0, 4. So what we could do is we could mess around here. I'm going to just make a little table. We want to start, let's try starting with 4, 0. Now this thing, the other thing too is there's nothing on here the way this was drawn. We don't know which way, whoops, I don't want that. We don't know which, I'm trying to go to my arrow. We don't know if we're going in a clockwise direction to make this epicycloid or if we're going in a counterclockwise to make the epicycloid. But we can figure that out. But let's say we're going to start at 4, 0. Godzilla! Anybody know what value of t, if we plug it in to x, gives us a 4, and plug it into y, gives us a 0? Yep. Yeah, just start with your quadrantal angles and see if that works. And it does. So when t is 0, x will be 5 minus 1, which is 4. And y will be 0 minus 0, which is 0. Oh, that works. Let's see what happens when we get to our next quadrantal angle, pi over 2. So if we go pi over 2, plug it into x, what do you get? And let's hope we get 4, not negative 4. When we plug pi over 2 into y, what do we get? Well, yeah, so like here, we know that sine of pi over 2 is 1, so this term is 5. Sine of 5 pi over 2, that's bigger than 2 pi. So sine of 5 pi over 2 is the same thing as sine of pi over 2, which is 1. 5 minus 1. Oh, it's 4. Look at that. So that's going to give us one petal. We can see symmetry in this picture. Let's just go 0 to pi over 2, and then multiply by 4. So we'll multiply by 4 and go from 0 to pi over 2. All right. One problem done. Now we have the other problem still of how do we integrate this thing? No calcul cheater. We're going to get to use yet one more identity. Yeah. You guys remember all your identities still, right? Anybody have a guess which identity? Double angle. Yep. And it's cosine. Let's do cosine 2u. Which one do you, because cosine 2u we had 3 choices. Which one do you think we're going to use? The squared. All 3 of them have squared. Let's just put all 3 of them up here because it's good to remember. Anybody remember one of them? 2 cosine squared u minus 1. And then cosine squared u minus. Yes. Okay. And one more. No. Kieran.
1 minus 2 sine squared.
Yeah, and I think you were about to give it to me too. Yeah, 1 minus 2 sine squared u. Only one of these is going to be helpful. Anybody have a guess? The squared one, yeah. The second one is not. And so inside the radical here, we have a 1 and cosine, not cosine squared. So we're actually going to not use this one because there's not even a 1 in it. It's going to be one of these two with the 1. And the idea is to get just something squared in here to cancel out with the square root. Yeah, so if I were to use the... So you guys want the sine squared u?
Yeah, then it's minus 1. 1 minus 1 plus 2 sine squared u. And then adding 1, you add 2, and then you're still squaring like 50 and plus whatever.
So let's see. If we solve for the squared term, let's see what we're left with on both of them. So on the top one, if we solved for the squared term, what would we be left with? So 2 cosine squared u equals add 1 onto both sides. You get cosine 2u plus 1. So this guy rewrites to that. If we solve for 2 sine squared u, so looking at the third one, what does 2 sine squared u equal? Yeah. So looking at both of these and comparing it to this, number 1 or number 2? Number 2. It's got the structure 1 minus cosine, 1 minus cosine. Yes. So that's what we're going to use. And when we go back in here, we got the 50 still. I'll put the square root on. So instead of u, we have 2t. Because if u was 2t, that would be cosine 4t, which is what we have. So that's going to be times 2 sine squared 2t. Oh, so much better now. Because, hey, that's actually kind of cool because we got the 50 times 2 in there also. I think we can take a square root of 100 also. Last I checked, we could, at least. Yeah, so now, whoa, look how nice this is. Oh, yeah. Actually, let me get rid of that. We're going to have the square root of 100, which is 10, so I'll factor that out. And then all we're left with is sine of 2t. Oh, sweet. We're almost there now. We're on the home stretch. Let's finish this up. Oh, we need a negative. Uh-oh, are we going to get a negative answer? That seems not right. Oh, look at that. No, we're not gonna. Ah! Perfect. Right at the bottom of the page. And look what a nice number. Godzilla. 40. Isn't that special? Whew. Any questions about that? Yes. Every single, well, this is short. I'm just kidding. No, I don't think everyone will be this long. I actually don't remember. I can open the homework up after this. We can scroll through it and just see. I really can't. I made the homework of solutions like, I don't know, 3 years ago? 4? I can't even remember what happened 5 minutes ago. of nice, actually. Yeah. Have you guys? I talk about this movie every year, so if you've had me before, you're like, oh my god, showing her, just stop. Have you seen the movie Memento?
Is that the one, the Inception one, the one that comes after?
It's. Are you thinking Tenet? It's trippy, but it's not Inception.
No, it's about the same time.
Yeah, it's backwards. So it's the guy that so his wife gets murdered, but while she gets murdered, he also suffers brain damage. So he can't retain any short-term memories anymore. So he meets you, and then 5 minutes later, it's like he'll forget who you are.
There's Tenet and Memento and Inception. Those are the three.
Yeah. And so there's that part, but then on top of that, it's told backwards. Like the first scene you see is the last scene. Like you think you know how the movie's going to end, but you don't. It's so trippy. And then it's like, then you see the scene that leads up to that scene. And then you see the scene that leads up. So it's all told backwards. So you have to pay attention. But did you like it, Greg? Yeah, it's really good. Really, really good. All right. So, any questions on this problem? I think it must be one of my favorite movies, too, because I bring it up every year. So, look at that. It's like magic. All right, here's bubble number 2. And I'm not actually going to do a speed problem with you, but let's look at this. Well, I'll let you write it down, and then we'll look at it. But to work it out, it's just like working out arc length, because it's using without the integral. We have a cloud to write down. Write the clouds. One day, my dream will be that all of you have, well, I'm not using an iPad anymore, but I would switch back to an iPad if all of you had iPads, and then I could just airdrop these things to you. Wouldn't that be wonderful? Yeah. It might be. I'm actually kind of jazzed about that. That would be so cool. Can you imagine teaching volume for the first time, and if I could have like a hologram? Yeah. And then you guys would hack the system so you could learn how to send messages to each other during class. It would be awesome. Exactly. Yeah, that's exactly what I was thinking of. Yeah. That is one of my all-time favorite books. I actually reread that so many times growing up that it fell apart. I had to buy a new copy. Ender's Game. And then have you read Ender's Shadow? Ender's Shadow is really, so it goes back and it's the same time period as Ender's Game, but it's from the perspective of Bean. It's really good. Yeah. And so you have a lot more backstory to Bean. Which is why when they made the movie, I mean, the movie was just so bad, but Bean was like this, he barely gets any, he's like this, he doesn't even matter in the movie, but Bean is like so important to Ender. Oh. Yeah. Have you ever read any of the other books?
I think I tried, and I didn't.
Speaker for the Dead I liked. Xenocide I got through it, but yeah. And then the only Shadow book I've read is Ender's Shadow. That was cool. I like that one.
That was the one where they were like all like hive mind stuff, right?
Where they're what?
It's like all the hive mind stuff, right?
Yeah, and the piggies, and they plant the trees, and yeah.
I think I read that one. Very, very big.
Oh, now I should reread that one. I haven't read that one as many times. I'm actually trying to read the Wheel of Time series right now, and that's a huge commitment. That's 13 books, and they're long. I'm on book 3 right now. All right, so looking at this, the only thing really to notice with speed is there's no integral, but it kind of makes sense. So this is like the conversation I know that we wanted to get into last time, and I'm like, there's like so much more to get into before that. So we know that speed is the change in distance over the change in time. And we now know how to find the distance, which is our arc length. So speed then will be the change in distance with respect to time, ds dt. So the derivative of this integral is just the integrand. And so, I mean, it wasn't like, anyway, that's it right there. So hopefully now, if you left last time going, still speed, what? Anyway, now we got it. So here it is. So like I said, I'm not going to do an example with speed because we just did an example with arc length, and it's pretty much the same kind of thing. You just don't have to integrate. Yay. So that brings us to surface area. Our last cloud. There you go. You can read that, right? Let me see if I can make this. Is that too small? Can you read that, though? Okay. And if you recall, from when we did surface area before, this is very similar to our surface area formulas from before. You may not remember, but surface area before was just 2 pi r times the arc length. And that's exactly what we have here. It's just our arc length is a different formula. So it's the same. So once you guys write this down, we'll do one more example on surface area. And that'll be that. Yay! Yeah. Oh, yeah. That can be scary. Actually, I don't think any of you have ever heard me yell at a class, have you? Yeah, you don't want to.
No.
I do have, though, when I have classes that I have to yell at, they always tell me, wow, it's amazing. You get really mad and you yell and you get really scary, and then like seconds later you're smiling and happy again. Which is true. Don't make me mad. You wouldn't like me when I'm mad. Thank you. He never says those lines in the Marvel MCU movies, does he? Ah. Does he? Don't make me mad. You wouldn't like me when I'm mad? Okay. I love the TV show. Oh no, the Incredible Hulk with Lou Ferrigno and Bill Bixby. Yeah, that's Lou Ferrigno. Lou Ferrigno actually is in one of the MCU movies. It is. It's the Incredible Hulk. He plays when Edward Norton is delivering the pizza to sneak into the lab, and he has to go through the security guard. Lou Ferrigno plays the security guard. A little Easter egg for you. From Incredible Hulk? The leader of what? Oh, I haven't read the comic book, so I don't know. Yeah. Does everybody have the first picture? Because I'll scroll up a little and then you can start writing down the problem. Oh, I guess I won't. I have to, it will only show one or the other. Okay, never mind. Anybody still need this? All right. So here's the problem. Lions and tigers and bears. Oh my. Now we could set this up with like discs, washers, or shells, maybe. I don't know. But why do that when we have parametric equations now? Right? It's easier as shells, washers, or discs. No. We'll only do it with parametric, but if anybody wants to for fun, then try using, well, we know it won't be a washer. So discs or shells, feel free. See if you get the same thing. Better watch out. Hello? Sometimes I just feel like I hear things, you know. It's weird. So you just think if this was like back in the day of like chalkboards and whiteboards. You remember whiteboards, right? Oh my God. Yep. I don't know anybody on campus. I don't even know if we have an overhead projector anywhere on campus. Yeah. That's called an overhead projector. So the one that could you could put a book underneath and it would show the book, but it was done like with light and lenses, not a digital camera. That's called, so that one's called an opaque projector. Yeah. Yep. I never used an opaque. I did use an overhead projector a few times. Nope. It was chalkboards or whiteboards. Yeah, I totally skipped over opaque projectors. I never did the dot cam. Yeah, because actually I've been using a tablet since 2005. Yeah. Windows gets a bad rap, but Windows was the first operating system to have. There were. I had this really cool Windows laptop that the top part would spin and then fold down. So it had the top. Yep. Yeah. And the only reason I remember 2005 is the other day I was cleaning up stuff and I actually found my receipt. So, yep. I don't know, Miss Rader still has it. The thing got, remember, I don't know if you remember when laptops would overheat and the fan would go off and it'd be really loud. Like this thing would sound like a jet engine was taking off. So I was going to get rid of it, but I asked Miss Rader if she wanted to try it, and she said, yeah, sure. I don't know how much she actually used it, but I gave it to her. I wonder if she still has it. I'll have to ask her. Alrighty, anyway, let's do this thing. So we know that when that pink thing rotates around the x-axis, it's going to make like a lens. You know, it's going to be kind of a little sliver of a sphere taken off. Anybody have an idea what you think the first thing is we got to do? Joshua? Yeah, I mean, these formulas, we're not actually going to find the whole arc length, but yeah, we have to do this square root thing. And I guess I should be looking at this one because we're rotating about the x-axis. So yeah, I'm going to have to find f prime of t, square it, x prime of t, square it, add them up, see what we get. So what's f prime of t? Yeah, that's another problem, huh? We don't have parametric equations. How about we start off with that? Let's find parametric equations for this circle. So, do you remember? What's the radius of the circle? 3. So you remember... Yes.
The circle with the radius r centered at the origin is r sine theta and r cosine theta.
Very good. Yeah, it's almost like you were reading that. You knew it so well. Yeah. And then we had the other one, too. So depending on which direction we're going in. So which direction are we going in? I want to go clockwise. Does it matter? Actually, I'm kidding. I don't care which way we go. Yeah. So we have those two different ones. We have the one with, that would be 3 sine t, 3 cosine t, or 3 cosine t, 3 sine t. It doesn't matter. The limits of integration will change depending on which way we go. And we're going to look at those. But yeah, somebody say sine or cosine? All right. We're going to go with 3 sine t, 3 cosine t. And then, yeah, why don't we go ahead and do then the next thing Joshua suggested. We know that x prime of t is 3 cosine t, so x prime of t squared is 9 cosine squared. Oh, this actually isn't so bad, is it? So then, x prime of t squared plus y prime of t squared. That's just 9 cosine squared t plus 9 sine squared t. What does that equal? Yeah, that's just 9. If you factor out the 9, you get cosine squared plus sine squared, which is 1. Oh, I don't know. Can we take the square root of 9, though? That's going to be tough. I know, right? So, to go back to your question, Adon, are they all going to be that long? Yeah, they don't have to be. All right. Surface area. 2 pi times the integral. We'll look at the limits in a moment. I got to put the r. What am I going to use for r? No. So r3 is the radius of the circle, but the radius, when we're looking at the surface area, yeah, we're going to look at y of t. So as we spin around, remember if you look at one slice, the radius of the one slice is going to be where I just wrote r, and that's going to move around. That's going to be based on whatever y of t is. So y of t for us is 3 cosine t. But then we have the square root of 9, which I know is 3 dt. So this is going to be pretty easy to do. We just have to figure out our limits now. So any questions so far? All right, noodle on it. See what you get for the limits. Anybody figure out the limits yet? These are a little easier. Yes. If we had used the other one, the other set of parametric equations for the circle, if we had done instead of 3 sine t, 3 cosine t, if we had started with 3 cosine t, 3 sine t, our limits would be different. We'd have a different thing for here. This part would still be the same. We'd still have 9 inside the radical. It would still be equal, though. It kind of takes care of itself. But yeah, it's going to be pi over 6, pi over 2, because sine of pi over 6, it's 1/2, times 3 is 3/2. Godzilla. Cosine of pi over 6 is root 3 over 2. 3 times that is 3 root 3 over 2. So that gives us this point here. And then pi over 2 will give us the 3, 0 that we need. Now, one thing I will say, and this is we're gonna see a lot more of this when we do polar, which will be in the next unit. It doesn't really show up yet. I mean, it could show up, but it's not going to show up really on this problem. But you do have to be careful with your limits. Sometimes, to go from here to here, I don't have a good example prepared for this. But let me see if I can explain this. There'll be plenty of times to show you in polar. We're not necessarily going from pi over 6 to pi over 2 because pi over 6 is smaller than pi over 2. But the reason why we're going from pi over 6 to pi over 2, I mean, partially it is because smaller to bigger, but the other thing you always do want to go smaller to bigger. But remember, I didn't have to plug in pi over 6 to get this to work. Couldn't I have also plugged in negative 11 pi over 6? That would give me the same ones. So how do I know which one to use? I mean, this one just seems more obvious, but if I did a negative 11 pi over 6, what would happen is I could start up there, but I might be going the other way around the circle. I'm not saying it happens on this time because I actually think it's actually going to just make us go around a couple of times. But you have to be careful about that. Are you actually getting the part that you want? So sometimes, for instance, maybe we get a pi over 2 and 3 pi over 2. And so we want to start at pi over 2 and then go to 3 pi over 2 because, well, pi over 2 is smaller than 3 pi over 2. But if we do that, sometimes it actually gets us going in the wrong direction. So we'd actually want to do negative pi over 2 to pi over 2. So you have to just start thinking about that. It'll become a much bigger focus when we do polar. So we'll look at more examples and stuff like that. That's just something to keep in mind. But now that we got this is super easy to go ahead and work out. Let's finish it up. If I factor out all those constants, I'm going to have 18 pi on the outside. That would just leave me with cosine on the inside. Antiderivative is sine. And then finally, let's see here. Sine of pi over 2 is 1. Sine of pi over 6 is 1/2. It is 9 pi. Dun, dun, dun. There we go. Any questions about that? That's the end of my story. Bye-bye, video.